So yes, I'm Robert Virding. I was originally a physicist. Way back when. Yeah, it was a lot of fun until I discovered programming. And then I wasn't a physicist anymore. Okay. Yeah, well. But I started working for Ericsson and eventually ended up in their computer science lab, where we did a lot of interesting things. Amongst other things, we developed Erlang. A number of us left around 1999 to form a company called Bluetail, which was one of the first companies outside Ericsson to build products using Erlang. Erlang had been open sourced in '98. This was in the middle of the IT boom, and it was a lot of fun and really weird in many ways. Then the IT boom ended. We'd been bought up by Nortel Networks, and they started cutting things, amongst other things, cutting us and me. And I started working for Swedish military procurement. Yeah, that's I thought it was very strange as well too. I had a lot of fun. We didn't do any programming. Military procurement doesn't do things; it buys things, right? But I had the pleasure of working with computer games in the military, so it wasn't too bad. Then 4.5 years ago, I started working for Erlang Solutions, so I came back into the Erlang fold officially. Some of the things I'll be talking about here are things I've done during that time. So the thing here is that, yeah, they say principal language expert. It depends which card I have, what I am, right? So I don't really know. But anyway, yes. So Erlang and multilingual systems. That's the whole idea of it here. And I think to start off is just want to say that we in the Erlang community, especially the Erlang developers, we're very great believers in things like no language is good at everything. Okay. This is not saying you can't program everything in any language. You can, right? But most languages are not good at everything. Yes, you can do all this stuff in C. If anyone's ever tried it, you only do it once. And if you can do it in C, of course you can do it in assembler, right? I mean, why bother going up when I can do things in assembler? And also the right tool for the job. So there are a large number of tools out there, or tools or languages or systems or whatever you want to call them, and they're good at doing different things. So you should use the one. If you have a specific set of things you want to do, pick the language that's best for that. And what you generally find is that in any large system, different parts of the system will have different requirements. So it's not always logical or sensible to try and program everything in one language. That can sometimes be conceptually difficult to convince people. It's not always easy, but I very strongly believe in this. Yeah. So we're going to look at a bit about, okay, so now we're going to look at programming, using Erlang, the Erlang system for doing different languages, and why you want to do that. So we're going upwards from the base system here. So we have the Beam, which is the Erlang virtual machine. We'll look at some of the properties of that. Then we'll look at different levels of languages. So I don't know what good names for them. I call it native languages. They're running on the Beam, and they're using the Beam as the Beam is intended to be used. And non-native languages, they're running on the Beam, but they're not doing what they're supposed to be doing. And then you've got external systems, right? And hopefully at the end, a little bit of discussion when you'd use them. So what is the Beam? First question here. So it's the name of the Erlang virtual machine, and what it is, it's a virtual machine to run Erlang. Really, that's exactly what it is. No more, no less. And like other virtual machines, it's designed for running something specific. I mean, if you take the JVM is designed for running Java. Then it depends what you can put on top of it within that base anyway. So what's the basis of the Beam, or the Erlang system? So what are the properties that Beam is trying to give you, right? And the first slide here, these are things about the Erlang system. And all these things have direct support in the Beam. So none of these things are built on top of it. So if you're looking at Erlang, you'll see a lot of things look like library calls, but all this stuff is built into the machine at a very low level. So there's support for lightweight massive concurrency. There's support for asynchronous communication. There's process isolation. The error handling primitives, they're all built into the machine and directly supported in the machine. Continuous evolution of the system, which in this case means being able to do hot code loading. Other people have mentioned that before. That again, that's primitives, so that's built into the machine. The soft real-time nature. Again, that was a requirement we had. That's built primitives, or the basis for that's built into the machine. And support for introspection and monitoring. So the things that Jose mentioned with the observer, the primitives for doing that, they're built into the machine. So there's support for introspecting into a running system, which was something very interesting for us, because we're working on these type of systems where you could not take the system down to look at it. So you want to be able to look at a running system in production and just introspect to see, is it behaving strangely? Is this process behaving strangely? Things like this for it. Now, most of those things are seldom what, if you're going to implement another language on top of it, are directly what you really worry about. Except for receiving messages, because we use pattern matching to select which messages you want to receive. And pattern matching is sort of more up at the language level. Right? Then you've got things which are more at language level. And again, all this stuff is built into the machine for support for doing this. So yeah, we have immutable data, of course. We have some direct support in the machine for doing pattern matching, of course. It's a functional language with support for that. So the top three are just sort of basic things you'll find in functional languages, nothing strange. We have a predefined set of data types. So one thing you cannot do is define your own data type. The system machine just doesn't support it. It has its own concept of a code, of modules, and how they work and what they can do and what they're supposed to do. You cannot get around that. Another one, there is no global data in the system at all. There's just a thing to get around. After a while, it becomes extremely natural. There's no problem with it, but the same thing. Same thing with all these. And these are the type of properties, if you're implementing a language on top of the beam, like Erlang, what you will exactly see. So what happens if you do want to add a new data type? So Erlang has something we call records. It's just a structure with name fields. But we can't do it. We have to fake it, right? Because there is no support in the Erlang machine for adding new data types. So we fake it. We use an existing data type, a tuple, and we have a special format, and we say that the first element of the tuple is the name of this record. And then you've got the field straight in there. So this is the way we do the new type. Right? We're just faking on top of the old type. Talking about languages here, which languages? In this case, basically anything. They can be config files, they can be DSLs, they can be real languages, anything. It doesn't really matter what we're talking about here. There is, in the Erlang system, or the Erlang OTP, there is a set of basic tools you can use to help you write languages. This is nothing strange. I mean, you'll find that in most other languages and systems as well. There's a lexical scanner generator. It's called Lex. It just happens to look very close to Lex. There's a YEK, a parser generator, an LALR1 parser generator, which pretty much does the same thing as YAK, but for the Erlang stuff as well. And there are other tools for building and working with code. There's XML parser, a couple of them, and of course there's the compiler for doing a lot of stuff as well. So the compiler's been designed in such a way you can input things and get things out of the compiler at different stages. You don't have to put a file in and get a file out. You can put code in at various levels and work things out for it. So this is quite nice. So what I plan now to look at first what I call the native languages, right? And what you end up is basically the new skins for an old ceremony. If nothing else, don't get anything else out of this talk. And if you hadn't heard that record by Leonard Cohen, go listen to it. It's great. It's fantastic. Right? So yes. So what this means here is that if you're going to implement a language sort of natively using the basic properties of the beam, you're going to end up with the same type of execution. At the lowest level, the same type of execution as you get in Erlang. Because that is what the beam is designed to implement. So the virtual machine and the language go very much together here. Now, you can put new syntax on top of it. You can do different packaging, but at the bottom level, this is what you get. And there's just no way around that. In that sense, the virtual machine is very unforgiving. Okay. And all of the facts I mentioned, the properties I mentioned, they're all very much interlaced with each other. So going in and changing something is really difficult to do because you'll affect everything else. For example, you might say, well, why can't I do mutable data? I mean, it can't be too difficult to put a fix in there to fix mutable data. Then you'll affect all the garbage collectors. You'll affect other properties of the process management and stuff like this as well too. So all these things all affect each other. Once you start fiddling with one thing, it spreads. So I'm just going to mention two languages here that are at this level. One is Elixir, which Jose was talking about this morning, and one I call LFE, which is Lisp flavored Erlang. And both of these work in sort of this level. They're a skin on top of the existing system. You have the Erlang virtual machine, the beam at the bottom. You have Erlang, you have OTP, which is a set of libraries for Erlang, a set of design patterns for how you use the language to build systems, things like this. They're all there. And then you put your new language, your new thing on top of that. So you have your new language, you'll have a new set of libraries, you'll have whatever you might be, but the base level you'll still have the same thing. And yeah, that's why the basic properties of the language end up being that. And you make full use of what you have there. I mean, there's been a lot of work into the libraries to make them usable for building reliable systems. And again, I can also say, getting back to the properties of the system and of the language, when we were designing the language, we were also thinking about how you would actually use it to build a system. So the features aren't in there just because we thought they were fun. That we're there because we felt that with those features you could build reliable systems on top of the language, using the language. So it's very much integrated with what's in the language and how you intend to use the language. Okay. So the first one I was going to mention is LFE, which is my baby. And the goal here was just to provide a Lisp with all the Lisp goodies you're used to having, right? So it's truly homoiconic, it has a real macros, Lisp macros, yeah. And it seamlessly interacts with vanilla Erlang and OTP, so you can use everything in there. You can use it together with OTP, so you can write modules in LFE, you can have modules in Erlang, and you can interact with them, everything like this. As many Lisps, it has a small base core language. A lot of things you see are macros. And seeing it's directly going down to Erlang, it's the same speed as writing things in Erlang. You're not paying anything extra for doing this. That meant it couldn't be any of the existing Lisps. It cannot be Common Lisp or can't be Scheme because they just don't have the properties or have other properties which the Erlang machine doesn't support. And the goal was not to extend the machine. So there's no mutable data, for example. We only have the standard data types. We have records, but that's nothing special there. We don't have, say, Common Lisp packages, namespace packages, because they just don't work in Erlang. We have the Erlang modules instead. Macros are compile time because the machine only supports a compiled code. So you can't have macros there. It's a Lisp 2 and Lisp instead of a Lisp 1. I'm not going to go into that here. And again, it's as fast as it. The other major alternative directly implemented on top as a native language is of course Elixir. And the quote from the homepage, it's a dynamic functional language designed for building scalable and maintainable applications. That's what it's designed for. It's, for those who have seen it or those who haven't seen it, it's influenced by Ruby, but it's definitely not Ruby on the Erlang VM. It has meta-programming capabilities by macros. They can't really play with the syntax, but otherwise you have a pretty good macro package there. And it has a lot of libraries and interfaces which have been standardized and rewritten. So if you want to compare it to LFE, it's a thicker skin than LFE is for it. Yeah. It's also been influenced, I think, quite a bit by Clojure as well, too. It's getting Clojure-type properties in there as well. So, for example, with the data types, okay, it has records, but I don't think they're really very much used. They're there, mainly I'm guessing just to interface Erlang necessary. But it has a concept called a struct. But I've just said you can't define a new data type. Structs, they're built on top of maps. and you have a special key, the underscore underscore struct underscore underscore key, which gives you the name of the struct, and that tells the Elixir system that this is not just a normal map, it's a struct instead, and gives you a set of operations for working on structs. Amongst other things, you can get compile time checking of the keys you're using, which is one very nice feature, one reason why you want it. Right? Yeah. So that's LFE and Elixir, and both have this problem that whatever you want to make it look like, at the bottom level you have this execution model. Then you on top of that you can put nice things to make it give you the properties you want and the features you want. You can add new libraries, you can add other features for it. You can of course do all your own packaging as well. That doesn't affect it. So yeah, so the next level I was going up is, okay, with languages still on the Erlang machine, but these are the ones I call not native languages, because we're going to go beyond what the Erlang machine directly gives us and add new functionality, add new semantics and new data types handling for it. So there are different semantics, different definitely non-Erlang data types, and non-Erlang handling of data. So here we're going to say, yes, we have these languages and they have these properties, and we're going to implement these properties. And these are two options I've done myself. There's one called Erlang, which is a Prolog implementation, and there's Lua, which is a Lua implementation, running on top of the Erlang machine. And the Erlang, it's a standard Prolog. You can go look up, it's a subset of standard Prologs. If you go look in the standard Prolog book, you can connect it directly to Erlang, and you can see everything like this. But of course, this has completely different semantics from Erlang. Okay, so Erlang's functional, Prolog's logic, and it has completely different semantics. So we have backtracking, we have logical variables, we have unification, and all these things. But there is no direct support at all for this in Erlang. So this is something you have to implement in your put in your language implementation on top of Erlang to get the language to work. Fortunately here, we have a pretty good mapping between Erlang and Erlang data types, except for logical variables, because they're sort of destructive, but they're not, and they do strange things. But so here what we've done is we've basically kept most of Erlang data, so data handling is pretty straightforward as is in Erlang, but we've put another semantics on top of it. We have to implement that. There are a number of ways you can do this. If anyone wants to talk about this later, but I hadn't planned to go through it now. But so here we're changing the semantics of the language, and it's a decidedly different semantics. The other one's Lua, and implements Lua, standard straight 5.2 Lua, straight out of the manual. And I like Lua. Okay, if I have to work with a non-functional language, I think it's a very nice little language. It's small, it's neat, it's imperative, it's dynamic, it's lexically scoped. It has mutable variables, it has mutable environments, it has global data, mutable global data, all the bad things, right? Yeah, after a while you get honestly, sorry, quick push, you get slightly surprised here. You get so used to working with immutable data, you sort of get surprised, mutable data, how do I actually use this in any sensible way, right? Well, if I do start modifying things, I'm going to start destroying things for someone else, right? I mean, if you haven't worked with immutable data, it's fantastic, because I know data will never change under my feet. Whatever anyone else does, if I have a reference to a bit of data, to a block of data, it will always be the same, and no one can ruin that for me. So having mutable data is really weird. Ooh, that was a bit better. Yeah. So what we have here is the semantics of the language pretty much follow Erlang. It's a simple functional language. So you can basically compile it almost compile it straight down into Erlang. The difficulty here is the data. Okay. So it's quite restricted in data types. There is a nil, which just means nothing. It's got booleans, it has true or false. It's got numbers, just floating point. I think the latest version has integers, but I'm not really certain if they're real integers or just floats that behave like integers. Have to check that. It has strings, which are immutable strings, just nothing straightforward, and then it's got tables. So all the difficult bits and the good bits are in mutable key value, global mutable key value tables. And they use tables for everything, right? It's for tables. It's for arrays. They use lists. Well, it's the kitchen sink as well. Everything's a table, right? And if I'm sharing a table between different parts of the program and I make a change in the table, those changes are visible everywhere, which is completely different from Erlang. So here the problem is not the semantics. That's pretty straightforward. Here the problem is managing the data in such a way which Lua requires. And it's actually quite a nice little language. They can do quite a lot with the tables, actually. It's not object-oriented, but you can write object-oriented code on it and define classes and class hierarchies and things like this because it has something called meta tables you can work around with. So you can do a lot of stuff in there. I think one of the major problems I see with it, there's a lot of things that aren't standardized and they've become very, very, and damn it, not to standardize them, right? So they don't really have one module way of defining modules. They have different ways of defining modules, which sort of work together or they don't. Right? But apart from that, it's a very nice language. So you have these two languages. You've got the Prolog, you've got the Lua, and they will not run directly on Erlang. The Prolog needs working with the semantics, and the Lua needs working with the data. But they're running on the system. Now we get to the third level. This is external systems. Now we're talking things that aren't directly running on the Erlang machine. And there are a number of ways of communicating with the outside world or communicating with a non-Erlang world. Right? So we have Erlang ports and sometimes as well something called linked-in drivers. We have NIFs, which are natively implemented functions. We have C nodes. So I can actually program other operating system processes to look like distributed Erlang nodes, and there's support for that. We could also, use UDP or TCP to talk to other things as well, but I'm not going to go through that. So yeah, starting Erlang ports. Okay, it's an interface to the outside world. This is actually the oldest mechanism we have in the language for communicating with the outside world. And it makes the outside world look like processes, look like Erlang processes. So sorry, I haven't mentioned this, but I mean, Erlang is very process-based. Basically, you do everything in processes. They're asynchronous communication. You send messages for communicating and sharing data in processes. Erlang ports make the outside world look like processes. So if you want to do something with the outside world, you send it a message. When something happens in the outside world, you'll get a message from it. So yeah, Erlang is very reactive in that sense. And we've been reactive for about 25 years, right? So we've been, yeah. So yeah, I love reactive programming, but I do not see the bit where it's new and innovative, to be honest. So yeah, we've been buzzword compliant for many years. Okay. And yeah, the Erlang ports behave like processes. I can send messages to them. The error handling works on the ports as well too. They're fail-safe. Okay. In the sense that if one of the external processes crashes, it's not going to crash my Erlang system. And one of the things you tend to become when you're working with Erlang, you tend to become very paranoid, right? If I do this, will that crash me? We're not talking about crashing a few Erlang processes. We're talking about crashing the Erlang system here. Erlang processes are fine, right? So yeah, this is very fail-safe because we're talking about other operating system processes. If they crash for some reason, the worst thing that'll happen is the port will get closed. Basically, you're sending byte streams. That's how you talk with the outside world. It's the most general thing we could dream up. You just send sequences of bytes to the outside world to stream. It's a Unix pipe or TCP connection socket. There is support for packetting these things. It's very basic. You can say, I want to packet my things with 1, 2, or 4 byte lengths in front of it, and it just does that. There is support for encoding and decoding Erlang data structures. So there's a bunch of C libraries, so I can actually send an Erlang data structure to it, and from the C side, I can unpack that and work with that. Just as a very simple example, but the most trivial one I could find here. This is just a small external C program which I could start up with a port and I could communicate with a port. So I would send it lines. It will read the lines in the get s, and it just print the line back to the standard output. So it will get input from Erlang on its standard input, and we'll send stuff back to Erlang on its standard output. We're just printing here. And after the printf, we have to do a flush, of course, to get the thing actually to send it out. And if if Erlang closes the port, then the standard input here will close, and the fgetS will return null, showing that it's closed. Then we'll just terminate this process and goes away. So this is extremely simple, about the simplest port process. On the Erlang side, you could do something like this. We can open it. There's an open port command, and this just says spawn. We're going to start an external operating system program. The interface is a stream, but we're actually putting a little bit of extra semantics on top. We've got some built-in line handling, so we're going to talk about 80-character long lines here. So we'll actually read lines. And this is just to make the last function a bit easier. So we can have an echo line function here. We give it a port, and the line I want to send to the port. The first line here, just the port, that just sends this message to the port. And the Erlang system will decide that, yeah, we're sending a message, and we'll take that line we sent out, the stream of characters we'll send out, and just send it off to the operating system process. And then we'll just sit and wait for the reply. Okay, so this is a stream. So there is no guarantee that we're going to get all the return values in a packet. And the other end, we're talking about the no guarantees that everything we send in one go, it will get as one packet of data. That's why we're using the fgetS, which actually reads until it gets a new line. So here we have to sit in a loop and read until we get the end of line. And that's what the first clause, the port, does there. Data. This is a bit of help we're getting from the port driver saying, yeah, now it's got a line. It's got the end of the line here, and this is all the bytes here. Then we'll just write it out. If we're getting characters from the second clause here, we're saying we're getting more characters. We'll append those to accumulator until we collect everything in the whole line, and then we'll just output it. So this is just a very simple code for doing these type of things. But you see here that the port it's just like a process. And like any other process, there's a protocol for communicating with. There's nothing strange about this. It just happens to be bytes. Okay, this is good, but sometimes you don't actually want to do something. I want a port, but I don't actually want to do it in another operating system process. So there's something called LinkedIn drivers, which just allows me to move functionality into the Erlang virtual machine. There's a predefined interface for doing that, and I can do that. And from the Erlang point of view, it behaves like a port. I open it in the same as it would be a port, but it just doesn't open the operating system thing. It does it internally. And it's usually, can be more efficient than normal ports because I actually don't have to send the data to another operating system process. I don't have to do context switches and everything like this. So that could be very good. The Erlang file system, the file interface, it works through LinkedIn drivers, for example. The problem here is there's no safety. Now, the LinkedIn drivers, their C code, they're running inside the Erlang emulator. If they make a mistake, the whole system crashes. So basically no safety nets when I'm running these type of things. So that's a trade-off. Yes, it's faster, but I'm offering safety. So it's a trade-off there for it. The second method are NIFs, they're natively implemented functions. And they allow me to implement functions in C, but to call them from Erlang as if they were Erlang functions. So it's a foreign function interface. Now, because I'm going to be calling them from Erlang, I'm going to be calling with Erlang data structures, and I'm expecting to get back Erlang data structures. So there's a large library for accessing the data structures, which allows me to access Erlang data structures. There is support for threads if I want to actually run other threads inside the Erlang operating system process as well from the NIFs. But again, there's no safety because this is just C code running in the emulator. If something goes wrong there, the whole thing just crashes straight down. But sometimes this is very nice. Sometimes what I want to do is a very C-based or function-based interface. And I have a bit of a small example here. This is real code, by the way. This is an I2C bus interface that runs on a Raspberry Pi. This is a couple of years old version. They've probably improved it since then. But this is a C function which I can then call from Erlang, which I'll show you on the next slide. And this is just how the interface looks here. So I call it, I have this env, which is just some form of Erlang environment. I get an argc saying many arguments this was called with, and I have an argv saying here's an array of the arguments. And what I first do is I unpack this array and check, am I getting 3 integers? That's what the first if does. I'm expecting to get 3 integers, unpack the integers and put them in FD, the file descriptor, the address and the length. That's what that does. If I don't do that, I'll return a bad arg. I'll return something which generates a bad arg argument from the Erlang side. Then the second bit, that is just the interface, the I2C drivers on the Pi. So I'm just setting which address I want to talk to, which file using the file descriptor, saying which address, I2C address I want, and then I'll just read this many bytes from that address. And then I'll build a binary, an Erlang data structure binary, and then I'll return that as return value from the function. And if something goes wrong in the IOCTL or the read, I'll just again just generate a bad arg error. So this is a real bit of C code. It's a very simple one. It's about the best I could fit into one page for doing things for it. Well, actually does something. This actually worked. This code actually worked. Right? There is more. In this package, there was something to write to the I2Cs to open and close them for them as well. So how do I call this from the Erlang side? So here we have a little loop I wrote to do these. So one problem here with this I2C interface, I can only do one thing at a time. The buses just happens to be 2 pins that are going to be flipped up and down all the time. So if I try to do multiple read and writes at the same time to that, then it's going to really bomb out completely. So I have to make sure that I'm only doing one thing at one time. In other languages, you might use a mutex to do that, so I could just block who's doing it. In Erlang, you tend not to use mutexes. Yeah, 5 minutes. I'll be done. And yeah, so what we have here is a loop, and the first 2 of the read and writes, they're just straight calls into it. The second one, I want to do requests. I want to send something off an address, wait a little bit and read. But I have to make sure no one else does anything at the same time, so I'm blocking this. I'm only having one Erlang process which accesses this O2C bus, and I sit in that request and wait. So I do the write, I sit and wait for a bit, and then do the read. The last one just is even more. That just, I can give it a list of requests I want to do is in one atomic operation. So this is just a typical way of interfacing the outside world in Erlang. You very seldom use mutexes for locking. You generally have a process you communicate with which goes through the outside world. So yeah. So the final one, C nodes. They're writing an external OS process that behaves like a distributed Erlang node. So use all the Erlang distribution mechanisms for them. And I can send using the normal Erlang distribution, normal Erlang sends to do that. It's fail-safe because we're running on a separate operating system processes. And it's a natural interface from Erlang because I'm sending and receiving messages with the outside node. And again, there is a large library for interfacing this from the other side and making it behave like an Erlang node, because an Erlang node expects certain things and getting data. I couldn't find a good small example for that, but if you go to this address, this colleague of mine, he's written a Lua interface using C nodes, running the standard Lua. So yeah, now very quickly. So why would I use which one? The native languages, of course, that gives me complete access to the Erlang and the VM, everything. It's definitely the fastest way to run code on the Erlang VM because I'm using as good as I can do it. The downside is I'm limited to what the language can do. Okay. The non-native languages, in this case the Prolog and the Lua, they've got good access to the VM. I might have to write more interface modules and stuff, but they're quite good accesses. It's very fast data transfer because they're still just inside the Erlang system like anything else. They are other languages. We haven't restricted ourselves here to Erlang in that sense. But generally, they'll be slower than the normal implementation of those languages outside. Although one guy was saying that my Lua implementation actually went faster than the standard Lua for some things, and I have to work out because they shouldn't do that, right? It shouldn't go fast. These, of course, can be costly to implement. Lua is a small language, and the Prolog is actually quite a small language as well, so that's quite good. But you wouldn't do something like Java in this, because it's just a sheer amount of doing things in Java. And that's why you have the external systems, of course. You can talk to anything. It's not just language systems. I can talk to other things in the world. I might have, for example, big applications or large set of libraries written in a certain language, and it's just completely infeasible to rewrite those in Erlang. either just the sheer work of it or for the efficiency, like doing the mathematical computations. Right? You just wouldn't do that in Erlang. You can, but you wouldn't. Right? Therefore, you'd Erlang to access the things, like Ericsson does. They do the signal processing in specialized hardware, but they're using Erlang to control and manage that, which is a very good split up for it. So you can monitor and manage systems. It's very good. Erlang's very good for monitoring other systems. We're sort of control freaks, so we like to keep control of other things, but we're very good at that. Downsides, generally slower interface. And it can be safe or unsafe whether I'm using a normal port, in which case it's safe, or I'm using a LinkedIn drive, in which case it'd be unsafe again. And yet we do worry about safety here. I mean, one reason you come to the Erlang ecosystem at all is it's for the concurrency and for building fault-tolerant systems. Therefore, you start worrying about if you can crash the whole machine. Nothing strange there. Okay, that's about it. That's me. And I'm generally very bad, as you've seen, of having pictures. I've got 2 pictures, so that's pretty good going for my talks, right? And I just had to do this, sorry. So, yeah. So, unfortunately, I could not fit the no cat in somewhere. So, yes. But, okay, that's it.